to make some contacts. I think it's working. Clark Snell is the author of 2 books on alternative to conventional construction, The Good House Book and Building Green. He's taught green building at the University of North Carolina, Asheville, and is a frequent lecturer here today.
I think Marcus and I were approached to do this panel, and we kind of pulled it together. We are both advocates of going further, what Matt was saying, towards carbon neutrality, and that's where the sexy thing came in, just to kind of trick you to coming. So let's get started. But the point of that is that we do need to make a step in a different direction, or a further direction, I think, than we've been doing so far. So I'm from a group called, I'm the managing director of the Now House Institute, which is a nonprofit. We have a group called the Now House Group that's a professional networking organization. And everything I'm talking about today you can find on the website if you want more details. So that what I'm going to do here is just create a context for what we're talking about on the panel today, basically carbon neutral construction, at least that's what I'm talking about. A quick review. The planet is getting warmer. That's the first thing that's happening. There's a bunch of other fun things that are going on. That's the big debate about exactly what's going to happen. It is our fault. It's not the bees or the bunnies. It's the humans. Big surprise. And though there's a lot of inputs, I think everybody knows this, but this is a 30-second thing. The main variable that's causing the climate change is carbon emissions. It does things like this, massive ice melts. So let's get beyond the debate, get over it, and see what we can do about it. It's a very complex question. Lots of back and forth about computer modeling, about what's going to happen. I think that gets in the way. Basically, it's a complex problem, but a simple solution. Carbon comes from burning fuels, so we need to stop burning fuels or cut way back. Our buildings are responsible for about 50% of our carbon footprint, and transportation, coming to and from work, moving stuff around, etc., is the next major chunk. So and that together is the built environment. So if we can make the built environment carbon neutral, we basically solve this problem. So a group of us got together. We've been doing this for several years. We said, okay, how can we make this happen? There's a bunch of initiatives out right now. The main one is Architecture 2030, setting benchmarks to get to carbon neutrality by 2050. We said, why don't we just do it right now? So we sat down, again, realizing that it's basically just efficiency. We're going to reduce carbon emissions by stopping burning fuel as much as we can within the built environment. We identified all the places that we thought that carbon was inputted or in the built environment where carbon was produced or was spent, and came up with this list. There's a similar list for transportation. And then we, after a bunch of research and different efforts, we're now building a prototype in West Asheville that we think is, has been energy modeled to be carbon neutral, basically by any definition. So what I want to do quickly is go through it and show you basically how we approached all those different variables one at a time. First off, we'll start with energy efficiency because it's the largest component. Basically, you can go back and forth with statistics, but about 90% of the carbon footprint and the energy footprint of a building comes from its heating, cooling, and plug loads. So our approach to energy efficiency is to build to the Passive House standard. Passive House is a German certification standard, probably the most rigorous in the world. The layperson's description is 80% more efficient than code. The way you do it, there's different ways, and it's basically a mechanically engineered system, so we can talk to Jeff more about it if anybody doesn't understand this explanation. But the simple way of putting it is you start with super insulation. Basically, we have R30 under our slab, where code is R0, R5, depending on where you live. Our value, in case anybody doesn't know, the higher it is, the better the insulation value. The walls are R40, basically. We're using a really interesting wall material I'll talk about in a minute called hempcrete. And the roof is about R70. Actually, we're getting about R85. The next thing you do is you put in really, really good windows. We're talking about windows that are a whole different echelon than what people are used to. Ours are coming from Sears Materials, an American company. A typical window is center of glass R2. Ours are between R7 and R11 based on the facing. And they're very airtight. The next thing we do is we build airtight. We're building about 10 times, there's about 10 times less air leakage in this building than sort of a a decently built code building, or maybe on the lower end of the green building echelon. Once you've done all that, then you can start talking about passive solar, and so solar heat gain and also interior heat gains. This building is designed to be, again, Passive House is basically an energy modeling program, so this is probably the most energy modeled residential building, at least that I've ever heard of. That I've ever been involved in. Anyway, it's been energy modeled to be heated by 18 people on the coldest day of the year. So in other words, if you're just sitting around on your ass watching TV with 18 friends, 17, you can heat your house. If you're going to dance around, you can probably do with 6, or get some big dogs, or a llama or something, and you can cut that down. Interior heat gains, like from computers, are also considered. So then, once you have that, you have a very, very tight building that can basically be heated and cooled with almost no energy. You have to then create air exchange. So we have an energy recovery ventilator, which is basically a high efficiency fan that can create air exchange with losing very little energy from that building, heating or cooling. So it's a simple technology that makes this possible. The whole point of all of that, in terms of carbon neutrality, you get to this point where then you're using almost no energy. Now we can afford a renewable energy system. In our situation, it's solar electric. To get to this is a multi-family home. Basically, it's got a one-bedroom apartment downstairs. It can be either configured as a large family home or split up. And even with 2 kitchens and 2 heating and cooling systems, it's a 2 kilowatt PV system to get to site net zero, which means that the house will create all its own energy. Then what you do to get to carbon neutrality, so in other words, we're able to do that because of the tiny energy usage. We get to 100% on-site energy production. Then with PV, with solar electric, you're not burning any fuel, so it's carbon neutral. Then we go beyond it, we put more PV on the roof, and we make extra energy that we put onto the grid that our neighbors can use, because basically when there's no one else using solar in your neighborhood, it just goes out your house and just goes right into their houses, basically, so it's very efficient. And we then allow them to use carbon neutral energy in their houses to some degree, and then that makes up for all the other carbon in the building besides just the energy, like materials that I'm getting ready to talk about. So again, this building's been designed already at this time, 2010, to be carbon neutral with a 6 kilowatt PV system, which is a pretty big system, but there are many houses that have that large of a system already, probably making 20% of their energy load. So that's energy efficiency. But the thing that we're doing that I think is a little different is we're looking at a bunch of other variables, and this is, to me, the sexy stuff. For example, materials. Turns out if you say, okay, our materials are going to have a carbon input. What's the best thing we can do? Well, local, site harvested, local, renewable materials, all the kind of natural building materials, straw bale, cobble, things everybody's heard of. If you're into that, are the best materials for that purpose. So we try to use as many of those as possible. We're using compressed earth blocks that we're making basically from dirt from the site or from nearby. You just compress the dirt with maybe a little bit of Portland cement in it.
That was great. That was sexy. I was gonna make a cock joke, but I'm not going to.